This webinar was actually initiated by Kostas Zakakais, who is an associate professor at Aarhus University, and myself, Max Halker, at Geophysical Imaging Partners. Started back at the conference in Bordeaux, where we had this first near-surface hydrogeophysical event, and where we had a special session on the future of instrumentation. At that event, Esben Auken gave a presentation on instrumentation, and we want to piggyback on that session and bring this into an open webinar, which is actually what's happening today, to continue that discussion, because we think there's a lot going on, and it's a very exciting future that we are looking into. This webinar is hosted by the technical community of the European Association of Geoscientists. And I also want to encourage you all to connect to the group here on LinkedIn. But first, a quick announcement here. Please remember to become a member of EAGE if you're not already a member. You can then benefit from all the papers, the journals, and other webinars that might not be for free here. Then I also want to pay your attention to this conference that's going to be held in the lovely Edinburgh in early September. There is a special focus on hydrogeophysics again. This is going to be the second time. Besides hydrogeophysics, there will also be a focus on the geotechnical part as well as offshore wind in the general session. Today's agenda here, we will start out with a keynote presentation by Esben Auken. It will be recorded and we will share the slides. If the recording turns out well, we might even share the recording. Then it will be followed by a panel discussion hosted by Pfaffhuber. And in the panel there will be Andrew Duncan and Kathy Chuffa. Then I will encourage all of you to ask questions in the chat. We will use the questions that are being posted there to facilitate the discussion afterwards. With that, I want to hand over the floor to you, Esben. So please share your presentation.
Okay, thank you very much. I hope this works clear, and I need to share my presentation here. Should be something like that, and I will do my uttermost to actually make this worth also recording. So thank you very much for inviting me to give this talk on near-surface geophysical instrumentation. This is something which is very close to my heart, and it can actually sometimes make me talk for hours, but here it will only be 15 minutes, so I will spare you for that. I'm now the CEO of Aarhus GeoInstruments, and before that I have been for many years a professor at the Hydrogeophysics group. I'm still associated with that as an adjunct professor. There are many people who have contributed significantly a lot from the Hydrogeophysics group and also from Aarhus GeoInstruments. So I think everybody should mute their microphones. Then it will work much better. My motivation for this talk will actually not start with talking about instruments, but I will try to give a motivation on what the problems we face in the world with water. This picture here is from Zambia. It's taken by one of my dear colleagues, Dennis Krumbacher, where he has been doing some work with support from the Paul Du Jensen Foundation. And it's basically illustrating the problems faced in many parts of the world with access to clean water, where we have often water holes like this, are in large distances to water sources. The collection of water from this source here is on the burden of the women and the children, and it's really a big problem for the gender equality, because women spend so much time of the day getting water where they could actually have done more useful thing in society. It's often an insufficient supply, and you can see here the protection is relatively poor. You just have that wooden fence around protecting animals and goats to enter into the water hole. Another problem with water like this is that it's you can see that the color of the water, it's full of silt and clay particles, and that grows bacteria. So this is really a very unsafe drinking water, and it causes water like this causes a lot of diseases in society. The picture to the right is from Togo. And that's the happy situation where there has been built a solar pump in the middle of a village. There are holding tanks that can be distribution networks in these villages. And with a water supply like this, there will be sufficient supply. It's convenient collecting points. As I said, it's in the middle of the village. And it's in that way, it's a safe water source. And it also helps a lot to grow the economy in societies with these relatively simple measures, because now women and children does not have to spend hours every day collecting water. This is one of my motivation factors, but there's also in the world we are a lot of stress on water, and many places people are talking about artificial aquifer recharge for a more sustainable water supply. So this is basically taking excess water from runoffs and storms and creating infiltration ponds and putting the water into the ground so it can be pumped out when it's needed. The movie here is from California with the project we did with Stanford University and the Tulare Water District. And this is basically mapping the subsurface of an infiltration pond. So basically creating images of how well can we get the water into the subsurface. And the other pictures or the other movies, this is from basically running between almond trees and mapping the subsurface here. So this is another application which is very much in demand worldwide. Before going into the details, I'd like, for those who are not so familiar with this technology, I like to compare it basically with a CRT scanner. If one get an injury in a knee, and you come to the hospital, the first thing the doctors do is not to start making surgery. They put you into a CRT scanner or an X-ray scanner, and then they can make a picture of the injury, and they can see where the problem is. They make an image of the knee, and they know what to do when they see that image. This is a simple explanation, right? But I hope you get my analogy here. And I like us with us creating these geoscanners, let's call them that, our geophysical instrument. They create images of the subsurface, and it should be like that. Before you go out and locate a well, before you go out and locate a new artificial infiltration sites or other things, one make an image, a scan of the subsurface, and you get an image of the subsurface. And then you know where to put your measure, put your well, make your artificial infiltration pond. Just a few words on I'm talking about groundwater here, and I'm pretty sure that most of you in the geoscience community has seen block diagrams like this. Of the water cycle. There is evaporation from rivers and oceans and lakes that goes into the clouds, and it falls as precipitation on the ground surface. Some of that water infiltrates into the ground, that becomes groundwater, and some of it is come out as runoff, and it goes out of runoff in streams and lakes. And this is the water cycle. But I'm pretty sure, so when I saw this block diagram here, I was looking at it, so there is an error here. and now I can't ask questions, so I'll have to do like a professor does. He asks the questions and then he answered he answered it himself. So basically, the problem in a block diagram like this here is that the ground is way too simple. We don't see the geological layers, and the geological layering in the subsurface is really controlling this groundwater flow. So it's extremely important that we have this information, and this is what we can provide with the geoscanners. In the global picture, water is becoming an increasing problem because of climate changes and also a growing population. So worldwide, about 1 billion people lack access to basic drinking water, and about 500 million people collect water from unprotected wells and springs, and another couple of million collect untreated surface water. And you can imagine how much diseases and how many problems water like this creates. Also, there is an estimate that about half of the world's population could be living in areas of high water stress by 2030. So there's really a lot of stuff to do for us. And that's where I think we as geoscience people, we have an obligation to provide good solutions, because we know how to do it, but I'm not really sure we are really doing it. So all images of the subsurface, they begins with data, and they begins with some instrument measuring those data. And all boreholes and all infiltrating ponds and all mappings, they begins with good images. This is how things are working together. I like you to think of the development in information technology. The picture here I found on the internet, and you see all these young people working with their cell phones. We all have cell phones, and that has really, since they were invented by Apple in 2007, that has changed our life. It has changed our society. It has changed how the world works and interacts and communicates together. And that development has driven, it has really made changes. But when I look at the geophysical instrumentation, it has not taken the same leapfrog in the last 10, 15 years. And I don't think it's too much to say that there are many instruments which are developed 10, 15, 20 years ago. I would just call that the past, and they are not really integrated with processing software and all the new things we can actually do today. And as an industry, and I will also say as a scientist, I believe that we are obliged and we can provide better solutions than what we are doing now. Just a little looking back, if I go back to the 1990s, that was when I was a student at the geoscience department at Aarhus University. At that time, we did single-site VES, and we have actually just gotten a fantastic tTEM instruments. At that time, it was really, really expensive. But methods at that time were characterized by low productions. And then the multi-channel ERT were invented in the mid-90s, and that was a huge step forward for resistivity methods. With airborne methods, there was really focus on mapping of mineralizations, really on anomaly detection at that time. Then in the 2000s, I don't think from the ground-based methods there was much different from the 1990s. There was conductivity meters where maybe you could say reinvented. There came out some really good conductivity meters. In the airborne, tTEM was starting to develop quite a lot, and we got really good quantitative or data which allowed for quantitative interpretations. And then in the 10s, continuous tTEM, that's our own instruments, very high resolution came, and on the airborne there was a very big development with more tTEM systems. But not at all something which is compared to what has happened in society with cell phones. So my wishes can be summarized as this. I really like to have that non-expert should standardly get subsurface images from complicated but yet simple instruments with integrated processing solutions. And here I like to emphasize that I like to work with non-experts. You should not be a professor or a PhD to work with geophysical instrumentation. It is something that many people with a basic training should be able to do. And this should be a standard process to make images and use these instruments and collect data. And then we have to make these complicated. It is a complicated physical process we are doing, but it can be made simple, especially if we really work with integrating processing, data processing solutions. And this is where to get here, we need small, reliable hardware boards, and we need compute power in the instruments used when we collect data. We need to integrate IoT, internet, tablets, and so on. And all this because of maybe the development on the cell phones and the information technology platform. This is all today not something we as instrument makers have to invent. We more have to find good and reliable boards and stick it into our instruments. So it's not that we have to reinvent or invent everything to do this. And then we need to integrate data processing software directly into the instrumentation while we collect the data. And I actually think that artificial intelligence can really play a big role in making these complicated things simple. And then we also need to reduce costs so that whenever we buy a geophysical instrument, we could as well have bought a Tesla. This is another discussion, but I really think we need to try to reduce cost of these instruments to get them out. And of course, we need to demonstrate, this is very, very important, we need to demonstrate clearly what society gains from the technology. And I actually don't think that's a problem, but we need to get it out there, and we need to get it to make it simple so we can get more users of our technology. tTEM, I will use tTEM as an example. It's a system I've been working a lot with since 2015 when we started to develop it. It creates high-resolution images of the subsurface, and it's used a lot for borehole siting, for managed aquifer recharge, characterization of contaminated sites, and so on and so on. And it gives a high spatial coverage and mapping in 3D. So you can say small pixels resolution, where maybe the airborne method, you can say they have a more coarse pixels, they cover large areas. We can cover small areas, but with a high resolution. And this is basically showing the system. It drives around 20 kilometers per hour, depending on the terrain. And we have a depth of investigation of 130, and also now with systems 180 meters. The front sledge is the transmitter that puts energy into the ground, and the receiver sledge is the white coil at the back, and that's what basically receives the signal from the subsurface. We run this with 20 meters between the lines and 10 meters between the soundings, so we actually obtain a full 3D coverage of the subsurface here. And these are some of the electronic components. There is a pump and a fan on the left top side, which is basically cooling things down. And then we have a quad-core computer, so a lot of compute power to process data. There is a transmitter and some other electronics in there. And boards at the bottom. I should have a scale here, but we're basically looking at boards of a size of, 5 by 8 centimeters or so on. So very, very small and modern electronics. And just to show here, what is it that the driver looks at? Basically, it's a tablet where we have a GIS system showing where we're driving. And this is what happens now. On the right side, there are the data curves, which basically show that we are collecting data. And at the bottom, we have real-time inverted data, where the blue colors would in this case be clays, and the purple and green colors, yellow colors, would be sand and gravel. This is a display we have on that. This is somebody should turn off their microphone, please. Maybe, yeah, thanks. So I'm just repeating my slides from before, and kind of my conclusion here is basically, I really think that geophysics for water will be key for mitigating the consequences of climate change. If we can get these instruments out there and get them used by many people, it will grow economy, not only for our own companies and for the geophysical community, but for society. And it will make a much better life and provide better opportunities for many, many people around the world. Yeah, thank you very much.